Are solid-state batteries really as safe as people claim? At first glance, you might think that ultra-fast charging would make them unstable or even dangerous. Surprisingly, the evidence suggests the opposite. During a demonstration of BYD's new Blade battery, engineers intentionally short-circuited the battery after it had already gone through 500 charging cycles. The outcome was remarkable. No explosion, no fire, and not even smoke, even after 2 hours. For many observers, tests like this lead to a bigger question. If battery technology is improving this quickly, could someone finally solve the major challenges that have limited modern batteries for decades? That question is one reason why a small startup called Donut Lab is starting to gain so much attention. According to discussions online, the company's so-called revolutionary battery could last up to 100,000 miles, recharge in only 5 minutes, and remain completely safe even at temperatures as high as 100 degrees Celsius. Naturally, the internet is fascinated. If you search for Donut Lab's battery technology, you'll find numerous videos and articles talking about its impressive performance claims. Some sources say the battery can charge at incredibly fast speeds. Others suggest it can survive temperatures that would normally damage or destroy conventional batteries. Then, there are the numbers related to energy density and lifespan, figures that sound almost too good to be true. This raises an important question. Is Donut Lab truly developing the next generation of batteries, or is this another case where excitement and hype are running ahead of reality? Before going further, there's an important update. Donut Lab recently released the results of its second independent battery test, and the results are unusual. Not because the battery failed, it didn't. In fact, something unexpected happened. According to the data, the battery actually delivered more capacity when exposed to extreme heat. During the test, the cells were heated to around 100 degrees Celsius and then discharged. Instead of losing performance like almost every conventional lithium-ion battery would, the battery performed better. This is where things start to become confusing, because the results don't clearly support either side of the debate. Critics believe the technology may be unrealistic or exaggerated. Supporters, however, believe Donut Lab might have created a breakthrough battery capable of transforming the electric vehicle industry. Strangely, this new test seems to challenge both viewpoints at the same time. When analysts examined the results more closely, they began noticing details that were not immediately obvious in the official report. Every data point was carefully reviewed. Calculations were performed on parameters that weren't directly mentioned. The battery's performance was also compared with nearly every commercial battery currently available on the market. The investigation didn't stop there. Researchers went deeper by reviewing academic studies, analyzing thermal performance data, and even examining the supply chain behind the materials used in the company's batteries. What they discovered opened the door to several intriguing possibilities, while also raising many new questions. Before exploring the technical tests in detail, it's helpful to understand what Donut Lab actually is. Donut Lab is a small startup based in Estonia and Finland that has made some extremely bold claims about its battery technology. According to the company, it has developed a solid-state battery that does not rely on lithium, a claim that immediately caught the attention of engineers around the world. The company says its battery could charge from 0% to 80% in just 5 minutes. It also claims the battery can survive up to 100,000 charge cycles, far exceeding the lifespan of current lithium-ion batteries. Donut Lab also states that its battery could achieve an energy density of 400 watt-hours per kilogram. If this figure is accurate, it would outperform most commercial electric vehicle batteries available today. To put that into perspective, many EV batteries currently operate in the range of 200 to 300 watt-hours per kilogram. Reaching 400 would represent a major breakthrough in energy storage technology. If all of these claims turn out to be true, the impact would be enormous. Electric vehicles could charge faster than it takes to refuel a gasoline car. range anxiety might nearly disappear, and battery packs could last for decades with minimal degradation. Of course, whenever a startup claims to achieve so many breakthroughs at once, skepticism is inevitable. This is why Donut Lab decided to start releasing independent test results. In an earlier experiment, the company partnered with Finland's National Research Center to evaluate one of its prototype battery cells. That first test quickly triggered debate because the battery showed a voltage profile that looked very similar to traditional lithium-ion batteries. The average discharge voltage recorded during the experiment was about 3.5 volts, which is typically associated with NMC lithium-ion batteries. This raised an important question. If the battery truly contains no lithium, why does its electrical behavior resemble lithium-ion cells so closely? That question remains one of the biggest mysteries surrounding this technology. Now a second test has been released, and this time the focus was on something even more dramatic. Before looking at the results, it's important to understand how the test was conducted. The experiment was performed by an independent research organization in Finland. However, their role was not to prove or disprove the technology itself. Their task was simply to test the device provided by Donut Lab and follow the testing procedures requested by the company. In other words, the researchers were verifying the measurements, not confirming the broader claims about the battery's chemistry. For the test, a single battery cell labeled DL2 was placed inside a climate chamber where temperature conditions could be precisely controlled. A 2.4 kilogram steel plate was placed on top of the battery to apply mechanical pressure during the experiment. This pressure was relatively small compared to what many solid-state batteries require, suggesting it was mainly used to prevent uneven heating rather than to affect the electrochemical reactions inside the cell. At room temperature, the battery was charged and discharged under normal conditions. During this baseline test, the cell delivered about 24.9 amp-hours of capacity. At this stage, nothing seemed unusual. However, things changed once the temperature started increasing. After the initial test, the temperature inside the climate chamber was raised to 80 degrees Celsius and maintained for 2 hours. The battery remained inside the chamber the entire time, so its internal components could fully stabilize at the higher temperature. Once the cell reached thermal equilibrium, it was discharged again. That's when something unexpected happened. Instead of losing capacity, something most batteries do at higher temperatures, the cell delivered 27.5 amp-hours. That equals roughly 110% of its room temperature capacity. In simple terms, the battery actually performed better when it was hotter. The researchers then pushed the test even further. The chamber temperature was increased again, this time reaching 100 degrees Celsius. Even under these extreme conditions, the Donut Lab battery continued operating. When the cell was discharged again, it delivered 27.6 amp-hours of capacity, still higher than the original room temperature measurement. However, the researchers noticed an important detail after the 100 degrees Celsius test. The battery pouch had lost its vacuum seal. Photos from the experiment showed that the pouch had visibly expanded, suggesting that gas had formed inside the cell or that the packaging material had weakened due to the intense heat. What makes this even more interesting is that despite the damaged pouch structure, the battery continued to function normally when it was charged again afterward. This observation could reveal something significant about the battery's internal chemistry. If the battery contained a typical lithium-ion electrolyte, a breach in the pouch at such high temperatures would normally cause serious problems. Traditional lithium-ion batteries use liquid electrolytes made from organic solvents, many of which are highly flammable. When temperatures approach 100 degrees Celsius, these solvents can start to vaporize. Combined with oxygen in the air and high heat, this creates conditions that can easily lead to combustion. So the big question is, how did Donut Lab's battery survive 100 degrees Celsius without any fire or failure? If the battery had used a conventional lithium-ion electrolyte, a damaged pouch at that temperature could have caused severe safety risks. Most lithium-ion batteries rely on liquid electrolytes that become unstable when heated. Under extreme conditions, these materials can evaporate and react with oxygen in the air, increasing the chance of fire. But in this case, none of that happened. Even after the pouch seal failed, the battery continued to operate normally. That observation alone suggests the internal chemistry of the donut lab cell might be fundamentally different from traditional lithium-ion batteries. Because of this possibility, researchers began taking a much closer look at the rest of the test data. As analysts reviewed the measurements in detail, several unusual patterns started to emerge. The first involved Coulombic efficiency, a key metric that compares how much electrical charge goes into a battery with how much energy can be taken out. It's one of the most important indicators of a battery's long-term health and stability. At room temperature, the donut lab cell achieved a Coulombic efficiency of about 99.82%, which is already impressive for a prototype battery. When the temperature was increased to 80 degrees Celsius, the efficiency dropped slightly to 99.18%. This small decline is expected because higher temperatures usually speed up minor side reactions inside battery materials. However, something interesting happened afterward. When the battery cooled back down and was tested again at room temperature, the efficiency rose to 99.88%. In other words, the battery appeared to recover from the thermal stress instead of suffering permanent damage. This is unusual. In most conventional lithium-ion batteries, repeated exposure to high temperatures slowly damages the electrolyte and internal structures, causing the efficiency to decline over time. The behavior seen here suggests that the donut lab battery may be using a different chemical system. Researchers noticed another unusual detail related to the battery's internal resistance. As the temperature increased from room temperature to 80 degrees Celsius, the internal resistance of the cell dropped by about 18%. At first glance, this seems normal. Higher temperatures usually allow ions to move more easily through the electrolyte, which lowers resistance. But there's an important detail. Typical lithium-ion batteries often show resistance reductions closer to 40% across a similar temperature range. The much smaller change seen in this test suggests that the electrolyte inside the donut lab cell might behave differently from the liquid electrolytes used in conventional lithium-ion batteries. These findings led researchers to consider another possibility. What if the battery doesn't use lithium at all? Initially, that idea seemed unlikely. Earlier testing showed an average discharge voltage of about 3.5 volts, which closely resembles the voltage profile of NMC lithium-ion batteries. Most sodium-ion batteries typically operate at lower voltages, around 2.8 to 3.1 volts, making them easy to distinguish from lithium systems. But deeper investigation revealed something interesting. Certain types of layered sodium-ion cathode materials can actually produce voltage curves that look very similar to lithium-ion NMC batteries. These materials can reach average discharge voltages close to 3.5 volts, and their discharge curves can appear smooth rather than stepped. This discovery opened the door to a new theory. If Donut Lab is using an advanced sodium-ion battery architecture, it could explain several of the unusual behaviors seen in the test results. Sodium-ion batteries are generally more thermally stable than lithium-ion cells. In many cases, their thermal runaway thresholds can exceed 130 degrees Celsius. Some experimental sodium-ion designs have even shown improved performance at higher temperatures, which could explain why the Donut Lab cell delivered more capacity at 80 degrees Celsius during testing. Another clue appeared while researchers examined the company's possible materials supply chain. Some references pointed to structures made from carbon nanotubes coated with titanium oxide, combined with a sodium-based electrolyte. Titanium oxide is already a well-known anode material in sodium-ion battery research. When paired with highly conductive carbon nanotube networks, it can form a structure that allows ions to move efficiently, even under demanding conditions. In theory, a design like this could produce exactly the kind of thermal behavior observed during the high-temperature tests. However, there is still a major problem with this explanation: energy density. The best commercial sodium-ion batteries available today typically reach around 160 to 175 watt-hours per kilogram. That's significantly lower than modern lithium-ion batteries used in electric vehicles. Yet Donut Lab claims its battery could achieve 400 watt-hours per kilogram, a number that would far exceed the performance of current sodium-ion technology. If that number is accurate, it would represent more than double the performance of current sodium-ion battery technology. That's why the mystery is still far from solved. Right now, the evidence points to a complicated situation. Some aspects of the battery's behavior don't match what we expect from traditional lithium-ion chemistry. At the same time, the company's claims go far beyond what sodium-ion batteries have been able to achieve so far. Because of this, the real answer might lie somewhere in between, or possibly in an entirely new type of hybrid battery architecture. So what do we actually know for sure? After 2 independent tests, several facts appear clear. The battery was able to survive exposure to 100 degrees Celsius while fully charged. It delivered more than 100% of its original capacity when operating at higher temperatures. It also continued functioning even after the battery pouch lost its seal. In addition, the efficiency and resistance patterns suggest that the internal chemistry might be different from that of standard lithium-ion batteries. However, many of the company's biggest claims still remain unverified. For example, the battery has never been publicly weighed, which means the claimed energy density of 400 watt-hours per kilogram cannot yet be confirmed. The tests conducted so far involved only 13 charge-discharge cycles, which is far below the 100,000 cycle lifespan the company claims. Another important detail is that the battery was never charged at high temperatures during the experiments. It was only discharged under those conditions. If the battery can truly charge safely at 100 degrees Celsius, that would be an extraordinary breakthrough. But until that test is performed, the question remains unanswered. At the moment, we know that at least 3 prototype cells have been sent for independent testing. 1 cell was used in the first experiment, another in the high-temperature test, and a 3rd prototype is reportedly planned for future testing. Some analysts believe the next experiment might examine low-temperature performance, possibly testing the battery at temperatures as low as -30 degrees Celsius. If the battery can truly operate across a wide range from -30 degrees Celsius to 100 degrees Celsius, it would significantly narrow down the possible battery chemistries involved and could represent one of the most impressive energy storage technologies ever demonstrated. For now, the industry remains carefully curious. In the world of energy technology, bold claims appear frequently, but real breakthroughs are much rarer. So the big question still stands. Is Donut Lab quietly developing the future of batteries? Or is this another example in the long history of ambitious energy startups promising more than science can realistically deliver? Fortunately, we may not have to wait too long to find out. If these batteries eventually start appearing inside real electric vehicles, engineers around the world will finally have the chance to examine them closely. And when that happens, the truth will be impossible to hide. It's difficult to imagine that a small startup in Finland could quietly solve the solid-state battery challenge, while large companies that have invested billions of dollars in research and development have yet to reach similar performance levels. This situation highlights an important scientific principle. Extraordinary claims require extraordinary evidence. In the case of Donut Lab, this principle is especially relevant. It serves as a reminder that strong proof is necessary to separate a true technological breakthrough from a simple illusion. By claiming to have developed a lithium-free battery with 400 watt-hours per kilogram energy density, a 5-minute charging time, and a lifespan of up to 100,000 cycles, Donut Lab is challenging many of the physical and chemical limits that battery researchers have worked with for decades. If these claims turn out to be true, the technology could solve many of the biggest problems facing the electric vehicle industry at once: driving range, charging speed, and long-term battery durability. So far, however, the available evidence is promising but not extraordinary. Test results reported by Finland's VTT Research Center show that the battery can operate stably at 100 degrees Celsius, which is certainly encouraging. But this alone does not confirm the more ambitious claims, such as 400 watt-hours per kilogram energy density or a 100,000 cycle lifespan. In science, the level of transparency should always match the boldness of the claim. When important details are missing, such as the actual weight of the battery cell, or when certain tests, like charging at very high temperatures, are avoided, it naturally creates uncertainty. To some people, it can feel a bit like watching a magician directing attention to one hand while the real trick is happening somewhere else. At the same time, history has shown that groundbreaking innovations sometimes come from small and unconventional teams. Because of that, the most sensible response isn't blind belief or immediate rejection, but a balanced approach built on cautious curiosity. With more independent testing and clearer, more transparent data, we'll eventually learn whether Donut Lab is truly developing the next generation of battery technology or simply presenting an ambitious concept that still has to overcome the limits of physics. So, what do you think about this technology? Feel free to share your thoughts in the comments below. Thanks for watching. If you enjoyed this video, make sure to subscribe so you don't miss our next update. It's coming in just 2 days. If you're interested in more exciting content about Tesla EVs or the Tesla bot, don't forget to like and share this video. Also, turn on notifications so you'll always be the first to know when we upload new videos. We truly appreciate your support and look forward to seeing you in the next one. Goodbye.